Please join me in welcoming our next speaker. He's being mic'd over there. Wes McKinney. Wes is a software architect at 2 Sigma Investments. But maybe more importantly, and equally important, is the fact that he was the creator of the Python's Panda library. And I think with that, I'm just going to let him come up and talk, read the rest of his bio here. And Wes, it's all yours.
Oh, I still have this.
Yep. Is it working? Okay. Three.
Yep.
Okay. Great. Does this thing work? Yes, okay. All right. Thanks for coming, or thanks for listening in advance. Who uses Python here? Just so I have a sense. Okay. That's changed a lot. I mean, it didn't used to be that way. I've done quite a few things over the last 10 years or so. I did start the Pandas project in April 2008. It was a closed source code base for the first year and a half of its life. But since then, I've been lucky to work in the Python community and building an ecosystem of data science and data manipulation tools for Python programmers. I work at 2 Sigma in New York. So if you are looking for a job working with lots of data, either in New York, London, Houston, let one of us know. In 2012, I wrote the book Python for Data Analysis. The second edition just headed to print last, what day? 2 weeks ago today. In the last few years, I've started to get more involved in the big data world, in the Apache Software Foundation, and I will tell you a little bit more about that during this talk. So I spend a lot of time thinking, particularly when it comes to the open source world, about how we can be acting more optimally, planning better, analyzing problems, understanding shared needs, shared use cases, and planning and building better software so that we can have better free software for data analysis and data science in the future. And certainly, a decade ago, things were a lot different. I started my career 10 years ago August, and I was immediately, I have a degree in pure mathematics, so I mostly wrote proofs as an undergrad. I wrote almost no code, and so I just randomly decided to take a job in the quant finance industry, thinking I would work there for a couple of years because I was a bit burned out after being a math undergrad, and thought, okay, I'll just go back to grad school after a couple of years. And one of the things that struck me was how difficult it was to do things with data. And so that's how I became inspired about building tools for working with data. But a lot has changed in the last 10 years. There weren't a lot of Python programmers doing statistics. The term data science didn't exist. Even R programmers using R instead of MATLAB or SAS was considered to be weird. So I'm excited with the way that things are looking right now. Sorry about my slides getting a bit messed up, but one of the biggest trends in the last 10 years is the general shift from closed source software to open source software. And this has been really great for the world in general. I would say it's a double-edged sword. On one hand, it's brought about significantly, all of the tools for doing data science are much more accessible. You don't have to write a check and buy MATLAB or buy SAS to do data analysis. You can install all of this software, through many different distribution providers on the internet, and so it's much easier to learn and use these tools for real-world applications than it was in the past. Another factor which maybe partially has driven this has been the cloud, where there's some days where maybe you want to run a job on one machine, some days 100 or 1,000, and so if you wanted to scale up your analysis, it wouldn't make sense to have to buy 1,000 MATLAB licenses just to be able to run that at-scale analysis just on that one day. So just the nature of open source software has made that type of work much more appealing. I would say one of the real risks and downsides of open source that we should all be thinking about as we go into the future is the broken economic relationship between the users of the software and the producers of the software. So it used to be when you bought MATLAB, you were paying for full-time maintainers to build and improve, document, fix bugs, to make the software better. So with open source software, hundreds of thousands of people around the world install pandas, but there's not exactly a wire transfer that shows up in my bank account to incentivize me to keep improving the software. One exciting thing that has come about has been tools on the front end part of data science, the presentation, interactive computing, and collaboration. So things like the Jupyter project. I know that not everyone loves the Jupyter notebook, but I think is part of a general trend of tools that facilitate sharing and collaboration around open science. And so to see these tools develop and be accessible, the infrastructure that created the Jupyter project started out in the Python world. And the Julia community and the Python community came together, worked on this, and now you can use Jupyter with over 40 programming languages. So that's very exciting to see. But I worry a lot. We have all of this great open source software, and we have some questions around sustainability and how to make sure that we keep improving and innovating on the software that we're using to do science. But there are many problems that we face in the coming years, and so I think a lot about how we can be planning better for the future. One of the biggest trends right now is all of the development in and around scalable machine learning, faster, better, more scalable machine learning, and so it's been really interesting to watch all of the major internet companies build machine learning and AI research labs and create open source projects for doing different kinds of machine learning. I guess deep learning ended up being a great marketing term, but it's great that they've built this software and they're giving it away for free. And they have many different reasons for doing that, but there's just been a huge amount of engineering firepower that's been poured into these machine learning problems. The hardware landscape has also changed a lot since I've been doing engineering in this space. So it used to be that disks were a lot slower. Processing was a lot more homogeneous. So we weren't doing general purpose programming on GPUs a decade ago. Now there are many different hardware targets where we can, there's even custom hardware for doing deep learning. So the way that we can build our systems to take advantage of hardware accelerations is going to require a lot of thinking and hard engineering. Memory has gotten a lot bigger and a lot faster. So all of the stuff that's happening right now with non-volatile memory, fast solid-state drives. So the fact that disk drives, CPUs haven't necessarily gotten 10 or 100 times faster, but our storage and memory has. And the amount of RAM that we have on machines, where it used to be that 16 gigs was a lot of RAM, but now you can get 2 terabytes of RAM or even more. So building our software so that we can take advantage of modern hardware, is imperative on us as a community. So one of the main problems that plagues me is the fact that while we have some pieces of software that we do share across programming languages and across computational ecosystems, there isn't a great deal of collaboration beyond some of the user interface and presentation layers. We do, of course, use the same file systems and databases and some of the same storage formats. But if you look at the computational libraries, the data manipulation frameworks, the statistics packages, which are used in any of these programming languages, there isn't a lot of collaboration. It's quite rare that you see Python and R programmers working together, or Java programmers and Python programmers working together. And so, what we see is that we're solving many of the same problems over and over without a lot of cross-pollination of ideas about design and architecture of these systems. And so, this isn't a comprehensive list, but some of the main problems that I've been thinking about and working on building software for fall into these 4 buckets around how we can get access to data. So take data from the way that it's stored and bring it into memory. How we manage that data in memory. So what are our data structures? I call them memory formats. Things like data frames. What do our libraries look like that we use to manipulate this data, to do data cleaning, data preparation, feature engineering, any of that data wrangling that happens en route to using a statistical model. And then, of course, there comes the modeling and advanced analytics libraries. So that's the machine learning frameworks, the stats libraries. And I see a lot of all of the really excitement these days has been accumulating in the area of advanced analytics. But really, I mean, we spend so much of our time solving all of these other problems that we have a lot of work to do to make these systems better. So one observation, if you just look at the Python world, particularly in the what I call the middleware part of the stack, so that's the data wrangling, data access, data manipulation, that there's a lot of vertical integration. And the pandas project alone has had to take upon itself solving a lot of these problems, completely, inside a single project. So we've written our own. We have our own CSV readers. We have our own access layers to databases, to file formats like HDF5. We've implemented our own versions of data frame manipulations and algorithms for dealing with missing data and all of that statistical computing business logic. We have basically a half-baked implementation of a SQL database, kind of in memory, doing group bys and kind of aggregations and so forth. If you look at any of the other ecosystems, it's very much the same. And so I've been thinking about this vertical integration problem in the context of improving the pandas project, which at nearly 10 years old has accumulated a lot of technical debt. And many of the heavy users of the project are aware, and these problems are faced in other languages as well. Some of the limitations around computational performance, particularly with modern hardware with lots of core and lots of RAM. The memory use is not very good. So my recommendation to users is that they have 5 to 10 times as much RAM as they have data. That often comes as a surprise, but it's not so fun when you're working with a large data set and you run out of memory. And I also, this graph came from a analysis of Stack Exchange data, Stack Overflow. I assume some of you use Stack Overflow to figure out how to do things. But so in the last couple of years, the Python programming language has become, at least according to Stack Overflow, has become the most popular language for data science. And additionally, if you narrow down to just Python, the Pandas project, at least in terms of question views, has had this meteoric rise and is now the most popular, most visited, most viewed Python package on Stack Exchange. And if you can read the legend up there, kind of the eye-popping statistic is that Pandas is driving nearly a single percentage point of traffic on Stack Overflow. So this is kind of mind-blowing that a tiny group of largely volunteer developers who've had very little funding and support for building this project have that we're now driving 1% of traffic on Stack Overflow because everyone wants to do data science in Python. So my thesis about what to do about this and to build a stronger and more future-proof ecosystem of technology for data science is to build some kind of software components that we can that lend themselves to reuse and that can be used across the different programming languages. So I'd like to talk about what those things might be and how we might actually go about building them. So as one observation, when you think about programming languages. Programming languages are really they're user interfaces for describing computation. So there need not be a tight coupling between the lines of Python or R code that you write and the way that that is translated into an algorithmic description of some data manipulations. So I think of this as, like, the metaphor I like to use is the iceberg model, where the part that you see is the part that's sticking above water, and it might be a relatively small part of the system, but there is a huge apparatus that you rely on that is largely unseen. So if you look at these are a couple of cherry-picked examples from R and Python, but even over time, the code that we are writing for manipulating data in these languages is starting to look basically the same. I just saw Hadley yesterday, and so we were talking about all of these things. But we've kind of independently arrived at this sort of grammar of data manipulation, these primitive operators for describing describing our analytics and our data cleaning and data manipulation. And so you can think about pandas or dplyr or any of these libraries as being sort of embedded domain-specific languages that you happen to use through the lens of the particular programming language you're using. But if you look under the hood, the way that this R code or this Python code, what it actually does, there's no overlap between any of the code. There's completely independent implementations. And so if I go and I want to make read CSV in Python faster, that benefits the R community not at all, and vice versa. So what I've been calling this effort is creating a shared runtime environment for doing data science. And so I'd like to tell you how I think we could build that. So one of my primary observations over the last 4 years is that probably the biggest barrier that's prevented sharing of implementations of algorithms and data manipulations is the fact that internally our data structures and our memory formats look different. So data frames in R look different than data frames in Python under the hood. Of course, the code you write is different, but if you look down, if you look at the way the memory is arranged in RAM, they're different. The way that we represent missing data is different. The way that we represent strings is different. So if I write an algorithm for Python, you can't use that and run it on data that's coming from R without performing a conversion. So to enable sharing of code between environments, you need to have a way to represent data that is portable across languages and that's not coupled to Python, not coupled to R, coupled to Java. A second part of this is that you need a way to describe data so that it can be moved easily between languages or between runtime environments. And that same technology also enables you to work with very large data sets on disk using memory maps, so zero copy memory map technology. So the idea is that if you have a megabyte of data or a terabyte of data on disk, you can, with a description of that data, you can access any value in that data set in constant time. You can select out any portion of interest, any columns of interest, and perform analysis on that data directly without having to go through a conversion step where you load that data into memory. And this has been one of the biggest problems with pandas, that the data is either all on disk or all in memory. And so that dichotomy causes a lot of problems for users. Assuming that you have portable data frames, portable memory formats, you need to build high-performance data access layers. So that's our read CSV type functions. There are plenty of other formats that we need to support, and the list of different sources of data as time goes on will grow longer and longer. But it would be really great to have a canonical, community-maintained, high-performance implementation, standard implementation of all of the different sources of data that we use, and so that we aren't all maintaining our own CSV readers and SQL readers and so forth. So the last part of this is it's not enough to have I/O and data interchange in a memory format. You need a computation engine which can be embedded and used in wherever you happen to be doing your work. So this needs to be a library that you can use in R, you can use in Python, you could wrap it in JNI and use it in Java. So this is a big project, in and of itself. I'm going to talk a little bit about it. But the idea is that a lot of the computations we do are very generic data manipulations, like adding two arrays or grouping a data frame and aggregating by some key. So those are primitive operators which you can implement and have a canonical implementation in your computation engine. But in many cases, you need to extend it with custom logic, which is defined in the host language in R, in Python. And so in extending the system with your custom logic, the overhead of doing that needs to be effectively zero. And one of the biggest problems in systems that provide extensions, some extension API in Python or R or a scripting language, is that the overhead for evaluating those functions is very high. And so if any of you use Apache Spark, you may be familiar with this, that the overhead for running R code or Python code inside the Spark runtime is very high. So a couple of years ago, I joined a group of open source developers to create a project to solve some of these problems, which I will briefly describe. It's called Apache Arrow. The idea is that we are creating a language-independent data frame format in memory that can be shared across runtime environments without conversion or serialization. So the idea is that rather than having to have this n choose 2, combinatorial explosion of data connectors, you can have a single memory format which is shared across your storage and data access and computational layers. This is hard because it's a chicken and egg problem, because everyone already has their own memory formats that all of their algorithms are implemented against. So by its nature, this is going to require a lot of work to build new systems which use Arrow, or build adapter layers into existing systems so that they can communicate with the outside world, using Arrow as one option for data interchange. So the things that we've prioritized in working on this project is making the memory layout for the data very efficient for CPUs. We also have some folks using Arrow on GPUs, so it's not just for CPUs, but the idea is that all of the data is arranged, maximized for data locality. So whether you're processing floating point numbers or strings, the data, the next value in a column is always next to the previous one in memory, and so that gives you a lot better processing efficiency. You can share it through shared memory. You can send it through a socket and read it without conversion. So that kind of zero copy mantra of like don't copy and convert, don't serialize, is kind of rooted in the project from the ground up. We spent a lot of time working on the metadata and the ability to describe different data types so that we can accommodate all of the different shapes and sizes of data that occur in the wild. Another part which I don't have a lot of time to talk about is we're doing the project in the Apache Software Foundation, and one of the reasons for that is that we want it to be a community-owned project that's developed in the open, and where we can grow a large community of collaborative developers, and it isn't led by a particular vendor or a particular programming language. So I assume some of you know that guy on the left, so Hadley Wickham and I got together at the beginning of last year, and just as the Arrow project was starting, and we created a small, simple file format called Feather. And the idea was that we would take Arrow data and put it on disk, and we wrote a library to read and write those files that worked in Python and R. And our goal with this was to socialize the idea of being able to very easily move data between the Python and R environments. And so I think that's helped kind of socialize the idea of having interoperable technology across the Python and R worlds. And so a lot of people were surprised even that Hadley and I were friends and that we would work together, because they perceive the Python and R communities as being like mortal enemies or something. we've gotten quite a bit of traction with the open source world. We've been working with the Spark community to build Arrow integration in Spark. There's a group of NVIDIA and some other database vendors have been building open source software for processing Arrow memory on graphics cards. There's a bunch of other projects where you can currently use Arrow in some shape or form. So one of my main goals in building this project is so that eventually I can fix Pandas's performance and memory use problems. And so if you think about performing data frame or array manipulations in Python, so here's an example of where we add two arrays and we compute the logarithm. So one of the major legs of work in the project that we'll be doing over the next couple of years is creating reusable libraries for evaluating these types of operator graphs on data that is coming out of data frames that have missing data and all of the things that we expect in data science languages. So we're going to build a library of kernel functions. So these are primitive operators that know about missing data, know about the Arrow memory format. We have operator nodes for describing all of those canonical data frame manipulations and data transformations. And then we'll build a query planner or a parallel runtime which can evaluate these types of analytics using all of the hardware that's available on the system. So if you have 16 cores, we'll use all 16 cores. But one of the things that we can do by building these operator graphs is that we can reason about the entire graph of computation. We can do things like, so here we add two arrays and we compute the logarithm. We can make the observation that the output type of add and log are the same, and so we can allocate one chunk of output memory and reuse that memory in between operators and achieve better processing efficiency by having less memory allocation. So plenty of work we can do, and there's lots of prior art. There's actually a lot of stuff happening in the deep learning world right now on graph data flow, and so I think we'll be able to reuse those ideas in kind of building an Arrow-based computation engine, multi-core task scheduling, operator fusion, kind of all this fun stuff you can do in building data flow systems. So the future architecture of the Pandas project, and this will take a number of years to completely build. Up until this point, we've been focused on defining a portable memory format and building data connectors for that format. The next stage of work is building this reusable native code execution engine, which could be used in Python or R or wherever you want. And then on top, we'll craft the API for that in Python, and we'll call that Pandas 2. And so this is what I would like the future to look like. But the best part of this is that we're planning to build all of this computational work in an open source project that has no strong coupling to Python. So it will be whenever anyone wants to go and build a Pandas-like project in another programming language, they'll have a strong stack of portable code that they can use as an embedded component in their system. So I know I threw a lot of information at you, but hopefully some interesting ideas and things to think about for the future. I seem to find myself attracted to these chicken and egg problems over the years, and I would say that the Arrow project and Pandas 2 is probably the biggest and most complicated chicken and egg problem that I've ever worked on, but perhaps one of the most important. And so, my view on these things is if you find a chicken and egg problem, the best thing you can do is be the chicken. So, join me in being the chicken and maybe write some patches. So, thank you.
I think we have room for a couple of questions over there. Yeah, the microphone is coming.
Yes, Wes, thank you for your talk. What's the timeline for Pandas 2, and will it be, fully backward compatible with Pandas? Or it's Pandas 3 that will be incompatible?
I think it will be backwards compatible with the good parts of Pandas. So I think we've accumulated plenty of things that we don't want to support forever. But I think as far as the timeline, I think the primary development of the computational system is going to be over the next 2 years. So I think we should have. I mean, I don't want to put a date on it, but we should have alpha builds for feedback. At some point next year. But as far as like production, a comprehensive production replacement or something that existing pandas users can migrate to is going to be a multi-year project, particularly given our thin resources. So I know that we're investing in it at 2 Sigma because scaling the Python data science stack is really important to us, and that's a big reason why I am there. But we are certainly looking to grow the developer community, and the more people we have involved in this effort, the faster it will go.
Like one more question.
Hey, so I want to know, like, how do you compare your work with Apache System ML?
Sorry, could you say that again?
So how do you compare your work with Apache System ML?
With Apache System ML. Well, I actually don't know that much about System ML. I will have to look into it. I will say the biggest divide between the Arrow world and the machine learning, deep learning world is that the data model is different. So we're working with tables and columnar data versus tensors. So the machine learning world is primarily tensor oriented. So if you follow PyTorch or TensorFlow or NNVM or any of the kind of latest gen stuff, that's all very kind of oriented at multidimensional array data, numerical data.
I think we'll break it here, and Wes will be around for a little while. When are you going to?
I'll stay for the. I have to go to the
break.
airport, but
Okay.
I'll be here for a half hour or so.
Please join me in thanking Wes again.